Good evening, everybody. I hope you're all doing well. Had a good weekend and your Monday wasn't too awful. Good. Mid. Okay. Looks like we got just about everybody here. Okay, so what we're doing tonight is the last lecture for the safety section of the review. And we'll start with radiation protection and then move into, I think, fluoroscopies after that. Okay, so starting with minimizing patient exposure. Uh, First thing we need to remember is as technologists, based on the standard of care and, of course, our code of ethics, is we need to understand that we are responsible ultimately for the amount of exposure that the patients are going to get and receive during their examinations. Um, Gone are the days where we had radiologists that would say, well, this isn't necessary. We'll go ahead and just do what the ordering physician wants. And instead of doing just a forearm, we end up doing a wrist, a forearm, and an elbow. And so, with that in mind, and knowing that, most facilities and most radiologists are just going to want you to do whatever it is that the ordering physician has requested instead of calling them and saying, hey, look, we can get it's our policy, our standard of care is to get both joints with the long bones. So it's redundant to order the wrist or the elbow unless that is actually the joint that is affected. So, with that in mind, remember that your technique determines the quantity and the quality of x-rays that are going to be used to generate our images. This is going to be the primary source of radiation for our patients. So the first technical factor that we have to consider is the KV. Are we using the correct KV uh, to get the quality of x-rays that we need to penetrate the part adequately? Now know that when we lower the KV, that's going to cause more absorption. Okay, differential absorption will go up. So the patient's going to receive more dose than if we used a higher KV. With a higher KV, we're going to have more penetration, which means more transmission through the part. The other two factors that we look at here are the MA and the time. Most commonly, we look at their product, which is mass. With our digital x-rays, we were able to increase our normal and our nominal KVs across the board on most of our examinations, which allowed us to drop the mass because of the detective quantum efficiency. In other words, because of how sensitive our digital systems are to radiation exposure, it allows us to drop our technique in the area of quantity being used. Now, more mass, of course, equates to more exposure for the patient and for the IR. And so by lowering the mass that we use, we decrease the patient's dose. The use of automatic exposure control, or the AEC, or an automatic exposure device, really does a lot to help guard against overexposures when we're dealing with patients. This is provided that we use the appropriate KV, of course, and that the machines are calibrated correctly. The thing about using the AEC, though, is that our positioning needs to be more accurate than it would be were we using manual techniques. When we use a set mass with a set KV, there's some latitude where we don't have to be directly in the center or over a specific area of the IR to ensure that the patient gets the correct exposure, because supposedly the mass that we set is correct for that patient. Now, using the AEC requires us to be much more accurate with our positioning. Now, because it does control the amount of radiation that actually reaches the IR, we do lower the repeat rate due to underexposure and overexposure. Although, remember that our computers now with digital really take up the work on that as far as getting us a diagnostic image. We can be off in our technique up to 10, 20, in some instances 50 times what we need in the exposure area and still generate a diagnostic image. And when we talk about exposure indices, I can elaborate a little bit more on that. Another method of reducing patient exposure, of course, is beam restriction and the use of devices that will limit the amount of primary radiation leaving the collimator housing and the X-ray tube. There's 3 different types, one of which has 2. We've got the diaphragm, the cylinder or cone, and then, of course, our collimators. Now, remember, beam restriction limits the area of tissue that we're going to irradiate. And so this helps to keep dose to a minimum. The smaller an area we irradiate, the less dose being transmitted to the patient. The aperture diaphragm is the simplest restrictor that we have. It's typically a flat piece of lead or a thick plate of steel with a hole cut in it. Now, it is non-adjustable except for maybe if you move it closer to the window of the X-ray tube or further away. Of course, they don't make an apparatus to do that. Usually the diaphragm is just stuck in between the collimator housing right beneath the area where the window is. And so any X-rays that deviate from that hole are, of course, absorbed by the surrounding metal, and any of the others that happen to be going in the correct direction, of course, are going to make it down to the IR through here. The next type of restrictor are cylinders and cones. These are long tubes of metal, either cylindrical in shape or conical in shape. And the cone typically corresponds to the beam divergence at a specific SID. And if we're going to use a cone, in most instances, it's going to be with a 40-inch SID. We typically don't use them with 72 inches. They can be used, the cylinder can be used at 72 inches, but again, most of the time it's for a close 40. Of course, the radiation field is going to be limited to the size of the diameter at the end of the restrictor. When we use a device like this, it's typically we're required to increase the amount of quantity we produce in the tube. So while we're limiting the tissue that we're exposing, it might be necessary to increase their dose just a hair uh, to make up for the amount of scatter that gets cleaned up when using these. Because, and it's not really that we're cleaning up scatter, we're not generating as much because we're not hitting as much tissue. The most common type of beam restrictor is, of course, our collimator and our collimator assembly. Two blades of, or two pairs of blades, lead plate that are adjustable within a housing and are accompanied by a collimator light. The light's off to the side and is reflected off the mirror, and it should correspond to the divergence of the x-rays coming from the focal spot, which means that the distance from the focal spot to the mirror is equal to the distance from the light to the mirror on the bottom side. If they're off any, then the light field and radiation field will not be congruent. Now, there is a general rule is your collimators should not be opened any larger than the size of the image receptor that you're using. And I know with a lot of the flat panel systems now, many times when you use the anatomically programmed radiography system for setting up the technique and getting ready to do the images, it will automatically collimate to a field size. Before, when we had multiple various IR sizes, we had what was known as positive beam restriction or positive beam limitation, or the PBL. And what that would do, once you put an IR in the bucky and locked it in and got the bucky and the cassette seated, the collimators would detect the size of the IR and automatically collimate down to whatever size it was and the particular orientation, either portrait or landscape. Now the APR is doing most of that work. This is the PBL that I was just explaining. Now we can override the PBL, just like everything that's automatic or, computer controlled or automatic in its adjustment. The technologist has the power and the ability to override that. Typically, it's not desired to go larger than the size of the IR, but you can always go smaller than the size of the IR as long as you don't clip any of the pertinent anatomy for that particular view. For our patients, um, accurate and effective positioning is going to reduce patient dose by reducing repeats, especially when we use the AEC. That's going to help a whole lot. We can also be proactive in their radiation protection by taking and placing radiosensitive organs further away from the primary beam. While not always practical, but it is a good idea in a lot of instances to do that. So even with it's been a couple of years now, they somehow said that it was okay to X-ray patients without shielding, and of course it's come back that that's not exactly what they meant. Shielding does help, and as long as we and really they rewrote it and described the rule in the same way that most programs have been teaching it for years, even back in '93. You can use a lead apron on your patient or lead shielding as long as it will not interfere with the procedure or uh, cover any anatomy. So, and they rewrote it. So over the spine and pelvis. Well, of course, we're not going to use it, um, especially over an abdomen. Uh, it's been about 4 years now. The ASRT, they got into a little bit of hot water with it because they put out this blanket statement and everybody jumped on it and said, well, we don't have to shield anymore. Shielding is not required. And that's not what they said, and that's not what they meant. So they had to go back and rewrite it, if you will. And we are still required to um, shield our patients. Um, if they are rather large, you can compress the tissue. When we did IVPs a lot, the abdomens, the stomachs would get big. You have beer gut or some sort like that. By reducing the thickness of the tissue with a compression band, we could reduce the amount of radiation that was required to make those exposures. And of course, anytime we reduce the amount of radiation we use, we're going to reduce the patient's overall dose. Another thing that helps with our repeat rate, especially, is interpersonal communication. We need to be able to put the patient at ease, uh, being able to have and carry on small talk, or at least being able to educate them a little bit about the process and what it is that we're doing, always seems to instill confidence in the patient for you. That's a benefit for you. It also makes them much more compliant. I try to not ask my patient if they can do something for me. I know it's polite to ask, can you put your chest up against the board? But I don't want to give them the option of saying no. So I will let them know that it is something that is required for the exam. So I need you to place your chest up against the board, as opposed to, can you put your chest up against the board? Or I need you to roll your hand over so that the palm is up, as opposed to, can you turn your hand over? It's always much better to be able to uh, have contact with your patient, use your hands. They're there for a reason. But by speaking to them and gaining their trust, providing them with a source of confidence in your abilities, is going to make the job so much easier, especially with patients that are outpatient of that type. Now, once we get into um, patients who either can't communicate, are unable to communicate, or are non-compliant, period, that's when our uh, adaptive radiology comes in, where we have to do things that aren't normal and kind of outside the box in order to get our images. For children, this is especially important. Um, Typically around the age of 5 and 6. For the most part, I try to leave parents out of the room. I find that when they're old enough to be able to communicate back and talk with you, that things go a lot easier if there's not an audience for them. Um, we definitely want to be careful protecting them from unnecessary exposure. This does mean using shields, um, higher KVs than we would have normally used with film or CR. Low mass techniques, being mindful of the amount of noise that's generated in those images. And of course, again, maintaining that communication, very, very important. Even with the parents, sometimes we want the parents in there, or we'll need them in there. And then other times it's a really big help if the parent waits outside. Um, one thing that I tell my intro students is that, with babies and infants, I always used to hear that, the baby's so strong, I can't hold them still. And really, the babies aren't that strong. It's that subconsciously, the parents or whoever it is that's assisting, or even the technologist, is afraid that the immobilization is going to harm the infant, and in it, so it just appeared. It just seems like they're strong, but they're really not. They're they're babies. Um, you just have to be firm and make sure to not make any sudden, quick uh, torquing type movements with them, and you'll be able to get them immobilized sufficiently to get your images. Since morbid obesity is a problem here in the United States, we have lots of patients with that high BMI. Because of that excess soft tissue, there is going to be more attenuation and more scatter that will be generated for those images. So it's very important that we understand and realize that when the patient gets large, the skeleton doesn't actually get large with them. That you're not there's no such thing as being big boned if you're uh, morbidly obese. That's all soft tissue. And as you can see in this image here, the pelvis is still the same size as you would have on a sthenic patient. Now, there may be a slight bit of magnification because of the increased OID from the excessive soft tissue, pulling the skeletal system further away from the IRs. But for the most part, your landmarks are still going to work and your centering is still going to be the way that it would be. You just might not have any light field off the side. Now, when we do patients with a high BMI, we are definitely going to need to increase our KV and our mass. And for a lot of these, we're going to want to use a grid. There we go. Another way that we protect our patients is with filtration. It's hard to know how much is overboard. In what terms? Going overboard with our collimation, or in technique? Um, Techniquing is tough. I will admit it's tough, and it takes a lot of work. And I know that as far as with the students that come through my program, it's not they don't get a lot of practice. The problem we have was digital. The computer gives us a beautiful contrast. It gives us a beautiful brightness because that's what it's programmed to do. So it manipulates the data and gives us a good image. Um, it's not like with film. With film, it was immediate feedback. As soon as you looked it up, it was either too dark or it was too light. The contrast was too high or it was too low, and a repeat was going to be necessary. And in most cases, as we'll discuss when we talk about exposure indices, um, we would want to err on the side of lower than high as far as technique goes. Um, Back to our protection though, filtration is important in that it removes excessively low x-rays from the primary beam. The filtration in most cases is going to be at the tube or beneath the collimator housing. This reduces the exposure to the skin and, of course, the organs as well, because we're getting rid of x-rays that on the best day, on blue skies, perfect weather, temperature, and hell has frozen over, those x-rays are not getting through that part, period. So rather than have them be absorbed by the skin of the patient or the organs of the patient, we use filtration to go ahead and get rid of them so that they don't interact with the patient at all. We absorb them. Aluminum is uh, the most prominent of filtration materials because it's easily shaped, it's readily accessible, and it's fairly inexpensive. Silicone can be used also as a filtration device, and sometimes we'll see that for compensation filters, which we'll talk about later as well. So a graphic representation, we've got here an emission spectrum with two separate exposures, one without filtration and one with filtration. Okay, the x-axis on an emissions spectrum is always the kV. It should be labeled, but it's typically your kV, where on the far right, the graph line touches the x-axis. That is the kVp that is set on the generator. Now, the X-ray beam intensity is the y-axis. So this is how much X-ray. So at any point on this graph, we're going to have a kV and follow it up to its corresponding number of X-rays at that energy. Okay, that's what this represents. And so when we have no filtration, you see we have a lot lower X-rays that are being produced, lower energy X-rays. There's still high energy X-rays being produced, again, no more than the peak that we set on the generator. But if we add aluminum filtration, we get rid of a lot of these X-rays. So from this graph, if we were to be very, very literal with it, we would say that from this X-ray energy, these are all the X-rays that are absorbed by our filtration. In fact, to be more accurate, these are all the X-rays that are absorbed by the filtration. But you can see the greatest amount that's being absorbed is at the lower end of the spectrum. Now, anytime we add filtration to an exposure, that is referred to as hardening the beam. Remember, we've got a heterogeneous beam, many different energies comprise it. And so by getting rid of those lower energy X-rays, we harden the beam. We increase the average penetrating ability of our X-ray exposure and beam at that point. Think of it as your school, your class average. Okay. Let's say you've got 13 assignments and you do 13 assignments and we make an average of those 13 assignments. That's going to give you a specific average, right? But if we take the lowest 3 grades and throw them out and average the 10 highest, the result was going to be higher than what you had with all 13 grades, right? So that is what we refer to as hardening the beam. We're increasing the energy because we're getting rid of so many of these lower energy X-rays. And again, we are getting rid of some of those higher ones, but we can always make up for that if we need to, right? Now for the NCRP, federal regulations state that inherently we should have, and actually it's not inherent, it's the total amount of aluminum filtration. We'll talk about that, but typically from your construction, the inherent filtration, which is the permanent part of the tube, this is the glass housing, the oil bath and the sand there, or actually it is the glass housing. It gives us 0.5 millimeters of aluminum equivalents in absorption and filtration. With the oil bath and any type of diaphragm that they put up here between the tube stand and the collimator housing, we're going to have another 1.0 millimeters. That on older machines is adjustable. Sometimes some of the older machines have filters that we can add or remove based on how much beam hardening we want to accomplish. The silver coating for the reflective portion of the mirror adds another 1.0 millimeters of aluminum equivalents, giving us a total of 2.5. And so for any diagnostic machine that is going to capable of being operated at 70 kV or more, the minimum requirement is 2.5 millimeters of aluminum equivalent. That will be checked at the factory based on their tolerances in the build, and it will be evaluated by a physicist once the equipment has been installed in a facility. It will be checked later as well at various intervals. We'll talk about the interval times during image production. But the minimum is going to be 2.5 millimeters of aluminum equivalent. Now, if you remember during X-ray production, the heating of the filament and prolonged heating of the filament, uh, lots of exposures in a short period of time can cause tungsten vaporization, and that gets deposited on the different components within the X-ray tube as well as the glass itself. So just that little bit of vapor that gets adhered to the inside of the glass causes an increase in the amount of inherent filtration in the tube. So as tubes get older, their beams are going to be much, much harder than they would be if it was brand new. Just because of the tungsten vaporization and the coating of the glass. But our minimum is 2.5 millimeters. Dose documentation. This is the responsibility of the technologist, typically during fluoro procedures. Now, the newer systems for both static radiography and fluoroscopy do record the doses in the data header for the images so that when it goes to PACS, that information is encoded in there as well. So, you know, you go to PACS, you could pull off or open like this. In this instance, you're going to open the hand that's been sent from the acquisition site on a PACS unit and find out how much dose was received or delivered for that particular exposure. For fluoro, um, again, the new systems do record that, but I still have several facilities here. When they do fluoro, they still keep a hard copy of that information. So they'll have a label that prints out, and if the machine doesn't automatically write it out for it, they will have a logbook that they can put the sticker in for the patient's information and the procedure, and then record the dose given as well as the fluoro time. Our receptors definitely influence the amount of radiation that we're going to use because we're able to use lower amounts. That is providing decrease in patient dose overall. There are times where we might use more radiation than you would think. And this is why in a lot of your digital systems, the ranges vary from body part to body part, and they're typically going to be, by comparison, they'll be higher for extremities that you would think than they are for larger body parts. And the reason for that is um, the amount of radiation that is presented to the receptor allows for um, a greater spatial resolution on the receptor, and we get better definition. So we're going to lose some of the noise that we would get for some of the larger body parts. We don't talk about film speed very much anymore. Um, but when we had film, we had cassettes that were at 100 for extremities, uh, 200 or 300 for thoracic work, and then we had our general radiography cassettes that were at 400. Now, the difference in those cassettes were the amount of radiation that you needed to get a specific density was varied. The faster or the bigger the number, the less radiation you would need to get a specific optical density or darkness in our image. So with extremities, we use the 100, which would allow us to use more radiation because we needed more so that we could get the fine details. 400 was great for general rad because we weren't looking at fine details. We were more or less looking at the big picture because that's what they were with big images, L spines, KUBs, pelvis. With chests, we kind of go somewhere in the middle with a thoracic setup. Otherwise, you could use a 400, and a lot of places did because it costs less to have two systems instead of three. But for this, just remember that the higher the screen speed or receptor speed, the less radiation that will be required for that image. Grids contribute to patient dose, and they contribute to an increase in patient dose because when we use grids, the higher the grid ratio, the more radiation we have to expose the image receptor to, which means, of course, more radiation to the patient. And remember, there's a formula for that. And in relation to the grid ratios, and I know that you're familiar with the frequencies as well in our grids, but there is no formula to go from one grid frequency to another grid frequency. Typically, the frequencies are going to be the same in a department. It's not often you're going to change one grid frequency for another grid frequency. You'll see more often than not a higher grid ratio or a lower grid ratio. And so that's why we have a formula for grid ratio conversions as opposed to one for frequencies. Any questions up to this point? Okay. All right, no worries then. Let's go. On to fluoroscopy. The systems have changed so much in the short amount of time. I don't know, for you guys, 31 years doesn't seem uh, like a short period of time, but for someone that's well beyond that, it is a short period of time. And when you think about the fact that the first fluoroscopy unit, was invented in 1896, is like 1 year after the discovery of X-ray. 30 years is not really that much. But in 30 years, we've gone from using zinc cadmium sulfide on a screen being held by a doctor at, pointing it at the patient with the x-ray tube behind the patient, having the x-rays come through the patient and hit that screen, and then standing at one end looking at it, to then mounting it in a system that went over the patient and using mirrors to bend the light that comes off the screen would go up and hit a mirror, and that would direct it to another mirror, which would direct it outside the tower and to another mirror for the radiologist to look at. I worked with one of those systems. I didn't get to see the fluoro because the radiologist was hogging the mirror. It was only, about a 4-inch mirror that he was looking at to see the fluoro. And so, I went from the mirror system to monitors with the image intensifier, and then subsequently to the television camera tube and CCDs. And now here we are with um, flat panel image receptors being used for fluoroscopy. Now, the good thing about that is because as we've improved the technology, the amount of radiation that's been needed for fluoro procedures has decreased. And it's decreased even more now that we're using what we refer to as pulsed fluoroscopy. With our older systems, the when the radiologist stepped on the pedal and we would get our image and watch the study until he removed his foot, that was a continuous stream of x-rays being put through the patient, running through the receptor, coming out, and then being able to visualize that on the monitor. During that whole time, the patient is being exposed. So moving with the pulsed fluoroscopy, where we turn the machine on and we make rapid exposures during a short period of time, we're able to decrease the amount of radiation that a patient will get during a fluoroscopy procedure. Now you can see the tube current increases the more that we pulse the machine. Okay, so with this one here, we're at 30 pulses per second. Well, 30 pulses per second just happens to be equivalent to the number of frames per second that is just beyond the human eye's ability to perceive. So when you flash an image at a 30th of a second, it looks continuous. Okay, so we're able to increase our MA, possibly drop the dose on our patients. And of course, we're going to reduce the amount of scatter that's being produced during those fluoro procedures as well. So technologists get a benefit from this as well. We can take it to 15 frames per second, 15 pulses per second, and in cath lab, intervascular, you can go down to 7.5 frames per second. Now, the images stutter for both that and the 15 pulses per second, but there's such a reduction in the amount of dose that the patients are getting that it's definitely a benefit. With fluoro, the exposure factors need to be high kV, low mass techniques. The newer machines are going to use 1.5 to 2 MA. Your older machines are going to use 3 to 5 MA. Grids can be used with fluoro, and again, they're going to be positioned above the patient, below the image intensifier if they're there. Anytime we have to use a grid, whether it be fluoro or static radiography, there's going to need to be an increase in technique. The positioning of the fluoroscopy unit does make a difference. We see this a little bit more with the mobile C-arms than we do with the fixed units. There is a little bit of movement that we're allowed to have, but based on the position of the tube underneath the table, we're kind of limited, not like we are with the C-arm. Most benefit for the patient and for us comes when the x-ray tube is placed beneath the patient. Okay, so the tube is below the patient and the receptor is above the patient. With these two limits here, 30 centimeters from the table to the receptor, and then 80 centimeters from the tube, our source, to the table where our patient is, we're going to get a dose 1.0 dose units. If we decrease, this is like decreasing your SID, okay? We're going to decrease the distance from the source to the patient and the table by 30 cms, and you can see the dose increases 4/10. If we increase our OID, moving the receptor further from the patient, here we've doubled it, and we've nearly doubled the dose that the patient is going to receive from that movement. Okay, so we would want as far from the source as we could possibly get, and as close to the receptor as we can get with the patient. This is going to provide them with the least amount of skin entrance dose, making the exam safer for them. Again, we've already spoken on time. Well, we spoke on dose and how it should be recorded. There's a timer on all the fluoro units that is set all over. It's 5 minutes. Okay. Once the timer goes off, the ability to produce X-rays and generate a fluoroscopic image ceases until the timer gets reset. And so because of that, the technologist is responsible for making sure that they remember how many times it was reset so that we can record accurate times and get accurate doses. And as you can see on this unit here, the air kerma listed here is for the procedure. And so typically, again, that'll be recorded to the header for the file and data that goes over to PACS. Now, the fluoro units have an automated aspect to them as well, in where it will control the exposure variables of KV and MA. Depending on the patient thickness, and it's like an AEC, it's looking for a certain amount of radiation, and it will hold the technique there for all subsequent images, especially with a pulsed system. You see this is evident in the use of the automatic brightness control, or the ABC. Happens when a patient, if we're doing an esophagram, a barium swallow on them, and the doctor has them kind of like in heads turned to the left, but they're still in an AP position, and they drink, and then the doctor will perhaps move them around to the lateral. You'll see that the anatomy will get really, really dark, and then it'll take a couple seconds, and then it'll pop back up, and then it'll look nice again. That's the ABC making the adjustment to the technique. A couple slides ago, we said we wanted the X-ray tube beneath the patient and the receptor above the patient. And this is the reason that we would prefer that to be the way it's oriented, because we have to be in the rooms too. And so when we're looking at this, this marks the exposure in this area at 12. This, just moving further away just a little bit, cuts that exposure in half. Moving back a little bit further, it cuts that exposure in half. But you see how the closer we are to the level of the X-ray tube, the further out those exposure levels go. Whereas at closer we are to the source, the quicker we get that change. So at this point at the tube, we're still at 12, but if we go straight vertically to the image receptor, right at the patient, we're almost in 3. We've decreased the exposure by a factor of 4, almost. So when we have it oriented the other way, that bloom occurs at eye level, thyroid level as well. So, you'd have to stand there like this in order to avoid that bloom of that exposure. Now, another advantage that we have with fluoroscopy is the magnification mode. And this, the field of view gets to magnified. In a dual field fluoro unit, we've got normal and mag 1. In a tri-field fluoro unit, we've got normal mode, mag 1, mag 2. Now, they can also be identified by the input diameter size. So a 23, 17, 12. We've got a 23 cm, a 17 cm, and a 12 cm input phosphor size that we can adjust to and from. Anytime we go into mag mode, though, we need to increase exposure to the patient. Because like collimation, when we collimate down to a smaller field, we have to increase exposure, right? So when we switch to mag mode, we're going to decrease the area and the size of the input phosphor that we're going to expose. That is going to require an increase in our technique. And in this instance, we're going to have an MA adjustment that will be performed. And this is all so that we maintain that same density throughout the tissue. Our air kerma, in fluoro, it's expressed as milligray per minute. This gives us an approximate skin dose where the beam is entering the patient, okay? So that's the location of the reading, and what it corresponds to is at that skin entrance dose. Another advantage is that last image hold. Moving into digital, we were able to use 2 monitors. And so we could take an image, or the radiologist could take an image and hold it on this monitor and still perform the exam utilizing this second monitor with this one being in place. With our older systems, that wasn't possible. We had one monitor in the room, and it just, if you wanted an image hold, you would just leave it where it was, where it stopped. That image would stay up there until you started the fluoro unit again. And then, of course, it would bring up the new image, so it was gone. This reduces patient dose because it keeps us from having to re-expose to check progress and see how things are moving along. Again, the documentation, PACS it's built into those. 5 minutes is the time limit. Our minimum source to skin distance has been established by CFR 21. For stationary X-ray units, these are the ones that are going to be in the rooms. Minimum source to object distance is 6 inches or 15 centimeters below the collimator. Okay, that's not below the source, that's below the collimator. Portable units, it is 12 inches. This is for static X-ray portables as well as C-arms. For stationary fluoro units, it is 15 inches. Okay, that's the minimum. That's how close it can be. No closer than 15, 12, or 6. And again, that's to reduce skin entrance dose. Now, the dose area product meter is a device that I have yet to see. I know it is located near the collimator. This calculates the dose for an area, a specific spot of our patient where our primary beam is directed. So it's calculated as product of the dose and the area of the beam, and the unit is milligray. That should be per centimeter squared, or it's actually milligray 2 centimeters squared. I don't know why the hyphen's there. That throws everything off. It's just to divide those units because it says product, it's the milligray times the centimeter squared. Moving into personnel protection. I'm sorry, not personal. And again, when we talk about ALARA, remember that ALARA came about as a means of educating technologists and keeping them safe. It happened to spill over, and the principles were easily applied to our patients. But ALARA is was primarily founded for the well-being of the technologist. Okay. Be mindful of our sources of radiation exposure. The first is the primary beam. Radiographers should never be in the primary beam or in the path of the primary beam. Okay. That means even after the patient, after the grid, after the image receptor, if the primary beam, if none of that stuff was there and the primary beam were to go all the way to the wall, you don't need to be in that spot. Okay. Remember time, distance, and shielding need to be practiced by the radiographer. As low as reasonably achievable applies to us. If you don't have to be in the room during the exposure, don't be in the room during the exposure. If you do, make sure you're wearing lead apron, make sure you stand in the correct area, put as much distance between you and the source, which is our patient. And again, don't be in there long. So leakage radiation comes out of the tube stand. Any cracks or crevices that are not covered by lead, there's a possibility of leakage radiation. So standing by the tube or behind the tube, even with portables, not a good idea. Then we have got the useful beam or our primary beam hitting our patient and then generating scatter. And then, of course, the remnant beam is what comes out of the patient. Scatter is the biggest occupational hazard, especially during fluoroscopy. Sorry. There is a limit for leakage radiation in a room measured at 1 meter from the x-ray tube. The exposure should not exceed 1 milligray per hour. Okay. Should not exceed 1 milligray per hour at 1 meter from the x-ray tube. Typically, your physicists come in when they go over and check the other aspects for QA and QC. This is one that they'll perform as well. Considering our patient as the source, if you need to be in the room, you need to be standing at 90-degree angle to, I know that says to the patient, but I mean, what angle are they using for that? It should be 90 degrees to the IR, okay, or the CR, right? So in this instance up here, moving, our source is here, and the X-ray is going in that direction. That is the CR, and so the amount of scatter being generated is greater the more parallel we are to the IR or to the CR, okay? At 90 degrees of the CR, we have less intensity and exposure here. Same thing with this one, okay? Our CR is going in this direction horizontally. The more parallel with the CR, the greater the exposure, the more at 90 degrees, the greater the angle, the less exposure we will have. So it's not really 90 degrees to the patient, it's 90 degrees to the CR. Cardinal rules: time, distance, and shielding. Time, minimize the amount of time that you are going to be in the room. And again, if you don't have to be, don't be. Distance, the inverse square law is our it's the leg that we stand on when we say get further away from the source. Okay? The further away we get, the least amount of exposure that we will have. You need to distance yourself as far from the source as possible. And there should be a minimum of 6 feet or 2 meters from the source of exposure whenever possible. Now, notice the word minimum, okay? We've had this discussion before in many of the other review classes. 6 feet is the minimum. That does not mean at 8 feet you're safe, or at 12 feet you're safe. In the Earth's atmosphere, X-rays have the capability of traveling 100 meters. Okay? There's not one ER, surgery suite, patient room, or X-ray room that large. So at any distance, you're going to get some level of exposure. There is no safe distance within a building for you to be from the source. Okay? There's just a minimum that you need to be. Shielding. Use of lead shielding. Anytime you need to be close to the source, use it for your, the aprons for your body, the thyroid shields, of course, for your thyroid. And if you can, or if you're going to be doing a lot of fluoro, maybe you're going to go work in the cath lab. If you can, if able to, get some glasses that have lead impregnated glass in them. You can buy them with or without a prescription, and take it from me, they'll come in handy. Now, as far as barriers go, we've got our primary and secondary barriers, leaded glass barriers, and then our personnel apparel. Okay. The primary barriers have a lead equivalent thickness of 1.6 millimeters, which is equivalent to 1/16 of an inch. That's pretty easy to get right there. 1.6 millimeters is equal to 1/16 of an inch. The primary barrier is the main wall that the X-ray tube will be pointed at for the majority of the procedures. Okay. This should extend 7 feet from the floor. And I know you've been in, and especially if you've been in rooms that have the ceiling support systems, some of those are very, very tall. Okay. Does not have to go all the way up to the ceiling, but it needs to be a minimum of 7 feet up from the floor. Now, this does say can potential or should be potentially strike. So we should have a primary barrier at the wall board. That's going to be considered primary. If you do a lot of cross tables, that could also be considered primary. If it's around the backside where we don't point the tube, then secondary barriers can be utilized there. The secondary barriers are half the size of the primary in thickness. So 0.8 millimeters in thickness or 1/32 of an inch for lead equivalents. Again, extending 7 feet up from the floor. And as they run into corners with primary barriers, they need to overlap. The control booth, it is considered a secondary barrier. So the booth itself only has to have 0.8 millimeters of lead equivalents. The lead glass window should be 1.5 millimeters of lead equivalents. Okay, so just a tenth of a millimeter shy of the primary barrier thickness. Should intercept only leakage and scatter radiation. We should never be pointing our tube towards the control booth barrier. Personnel should have personal apparel. And for lead aprons, we're looking at least 0.25 millimeters for general use. Some states require 0.5 for fluoroscopy. Okay, so that's just going to be vary from state to state. The minimum is 0.25 millimeters of lead equivalents. These aprons need to be hung. They don't need to be folded. Um, want to prevent creases and cracking of the absorbing material. These are also considered secondary barriers. Should not use them to protect from the primary beam. Now, that said, we do use them for patients. We do use them to shield patients. In a lot of cases, though, when we're using them, they are not within the primary beam. And for digital, they really don't need to be in the primary beam. We need to be collimating down and then shielding just underneath the collimated portion, if possible. Lead gloves, 0.25 millimeters of lead equivalents, same as thyroid shield and your glasses. So there's a lot of apparel, there's a lot of different things, but there's only a very, very few thickness requirements. So here we have um, a percentage of absorption for different devices at different kV levels. Okay. Remember that the x-rays are high enough in energy, they're going to go through the lead. And I know you've seen this, especially annually, when they go to check aprons. Typically, they'll fluoro them, right? They shouldn't do that. We'll talk about that later. But obviously, primary beam X radiation can get through lead aprons. So at 0.25 and 50 kV primary beam, 97% of the X-rays will be attenuated. Okay, but once we go to 75, that percentage drops to 66%. And at 100 kVp, just over half of the radiation will be absorbed. Okay, the other half is going to go through it. And of course, that changes as we go through the thicknesses. And even at 1.0 in lead thickness, we still don't see 100% here. Okay, so there's always a chance something's going to get through. Yes, gloves, glasses, and thyroid are 0.25 millimeters. That's slide 46. I wonder if they changed it recently. Which book is that? First, is it a textbook or is it a workbook? Okay, the rad protection book. Okay. Okay. Correct that on the slide then. We'll go with that. we got more than one source saying 0.35, that's what we'll go with for glasses. Now, if you see a question and they have 0.25 and 0.35 and 0.4 and 0.15, go with the 0.35. But if you get one and it doesn't have 0.35, but 0.25 is there, pick the 0.25. It'll be more correct than any of the others. Hopefully you won't run into that though. I hate it when we make test questions like that. All right, so here's a chart that breaks all that down for you or organizes it for you. So this is a good one to use. And of course, these are the minimums for the NCRP, number 102. And I'm going to go back and look and make sure. Go ahead and change again for the glasses. It's not there on this chart. The leaded glass is for the control booth. Mobile units should stand a minimum of 2 meters away. You do need to wear a lead apron. Stand at a right angle to the primary beam, if possible. So in this one, this bottom picture here, exactly why we're using it, I guess because it's standing at 90 degrees to the CR, but they're as far as that thing can go. That curly line is there. It goes out far. We need to go use it as far away as possible. But even so, this guy needs to be wearing a lead apron. Just because you've got the curlicue stretched as far as it'll go doesn't mean you're safe. For fluoroscopy, the protective drape on the units is not for the patient. That is for anyone standing table side at the control area for the fluoro unit. And unlike the C-arm, because we've got this housing here, we're not getting as big a bloom down here below as we do with the C-arm because of the metal that the table's made of, obviously. But you see how we've got this, as we get further away from the unit, the level drastically decreases, again, because of the inverse square law. Putting up the protective curtain, though, where we would have to be 1, 2, 3, almost 4 units away, we can be within 1 unit of the patient here, distance-wise, and be at that same dose level just from that protective curtain. The Bucky slot cover also helps with protecting technologists and the radiologists. It's hinged. Most units are going to be hinged on both sides, so you could slide it the other way towards the head if you needed to. And it still cover that. And of course, if you don't have fluoroscopy, then there typically isn't a cover. That's going to be 2.5 millimeters of lead equivalents. Because lead is so malleable, this typically isn't going to be made of lead. It's going to be made of steel, but its thickness would be, it would have the same absorption properties as 0.25 millimeters of lead. Obviously, it's going to be thicker. Remember, we've got the timer. 5 minutes is what it's set for. The machine shuts off and you got to reset it. New systems that you've seen or may have seen, these are popular in surgery suites, especially for urologists, cysto rooms. where they have a remote controlled fluoroscopy. This is going to orient the image receptor below the patient and the tube above. And we're like, well, remember there's a bloom. Why are we going to do that? This is remote controlled. There's not going to be a technologist or a doctor in the room when this is being used. If they are going to be in the room, because I've seen some that the controls are tethered to the unit. And of course, because there's a wire, there's only so far away they can get. There should be a movable barrier that comes in or is placed in the room between the controls and the patient. Again, advances galore in the last 30 years. Here is your exposure rates for fluoro. General purpose fluoro, we're limiting our patients to 100 milligray per minute. Non-image intensified, 50 milligray per minute, because we don't need as much radiation with non-image intensified. The high level controlled fluoroscopy, 200 milligray per minute. This is going to be your specialty cath lab interventional type systems. The exposure switch, remember, is a dead man switch. If the pressure is released, X-rays will stop being produced. It's designed this way for a reason. Stand back, minimum of 2 meters. For our personnel exposure monitoring, we have dosimeters. This chart illustrates the 4 different types of dosimeters: the film badge, the thermoluminescent, optically stimulated luminescent, and the pocket ionizing chamber. I'm sorry. The materials that they're each comprised of. Of course, with the film badge, definitely had radiographic film in it. How it's processed, well, we use chemicals to process it, and then we get the readings using a dosimeter. Or, sorry, not a dosimeter, a densitometer. The film comes out, it's got specific areas where there were filters, so we could determine the amount and the type of amount of exposure through certain thicknesses. And we use a densitometer to measure the light coming through. The less light, the more exposure that was received. Because it is film, it's got a silver halide emulsion on it. There's an expiration date on film, and it is very, very accurate. So 1 month monitoring period for film. Fairly sensitive. I mean, 0.1 millisieverts. That's pretty sensitive. Very economical. The dosimeter film itself can be kept in the facility or by the facility as a record. Disadvantages, though: high temps and humidity, leaving it in your car, especially in Texas, can cause inaccurate readings. Wearing it longer than a month, because degradation of silver halide can occur, can yield inaccurate readings as well. The TDLs, pretty nice. Uses the lithium fluoride. Those crystals, once sent in, they're heated, and there's a light that's given off. The light and the amount of light is measured, corresponds to the readings. They can be used for 3 months straight. They're twice as sensitive as film, not affected by humidity or temperature. The crystals can be reused, which means once they've been heated and the energy's been taken out of them and they cool, they're reset for use again. High initial costs. They're very, very expensive. The systems to get all of the equipment, especially the reader. And they can only you can only read them once. If you've got a record on film, you can take that piece of film and use the densitometer and read it again. But once these crystals are heated, the energy is emitted from them and it's gone. The OSLs, I would say the majority of facilities, especially hospitals, have gone to OSL using the aluminum oxide, processed with a laser light, worn for uh, a year. But it's more common that they're exchanged monthly, bi-monthly, or quarterly. Sensitive, 5 times more sensitive than the TDLs. Not affected by humidity, temperature. They have that 0.01 millisieverts of sensitivity. They can be worn for longer. If there's an issue during reading, they can be reanalyzed and read again. Problem is, you got to ship them off because typically you're not going to have an in-house reader. And because of the length of time that they can be worn, it's difficult to pinpoint a specific day that the exposures happened or occurred on. The pocket ionizing chamber, pen shaped, you keep it in your pockets. If you feel like you've been exposed, you just go to the electrometer and insert it into the electrometer and you can get the reading, because they do need to be read daily anyway. They are the most sensitive. We don't have a number for their sensitivity, but we get immediate readout, extremely accurate, very, very sensitive, but super expensive. And again, they must be read daily. And unless you write that down, um, you're not going to have a permanent record. TDLs used mostly in nuke med. That depends on the facility and how frequently they do, what the workload is for nuke med. Most of the facilities that I have here in East Texas, they don't have this huge workload. So um, they're using OSLs as well, and the finger uh, detectors and dosimeters. And part of the reason, again, is, East Texas, they're cheap here. Proper use of dosimeters. If a person runs the risk of receiving 10% of that annual occupational exposure, if that's likely, then they should have dosimeters. Now, it's not likely for the person doing x-rays in a dental office to receive that much exposure. Um, Even though they do x-rays every day, et cetera, et cetera, et cetera, the amount of KV that's utilized, the amount of mass that's utilized, and the extremely tight collimation that's utilized for dental x-rays, it doesn't warrant the expense of personnel monitoring. And in a lot of cases, it doesn't warrant shielding. Now remember that the dosimeters do not prevent exposure. I don't know why that says dose. I need to make a note to change that. Does not prevent exposure. It's only used to detect exposures. These do provide an indication of the work habits and the working conditions of a department and the people in that department. Um, this records only the exposure received in the area in which it's worn. Most of the badges for my students are neck badges, so they have to be worn at the collar level. and they need to be worn outside of any protective equipment. Okay, because the protective equipment's protecting you. We want to know what your exposure is when you're unprotected. So it needs to be outside any of those devices. They need to be kept in a safe place. Preferable that you leave them in your departments rather than in your car. Definitely keep them away from sources of radiation. Don't go to a tanning bed or a tanning salon straight after work and take your badge in there. I did have a friend who was a nuclear med technologist that actually did that, did an experiment and took a dosimeter and put it on the wall inside a tanning bed, and it did come back with readings on it. Um, there's going to be a control badge to go along with each individual's badge, and that needs to be kept in an area where X radiation and exposure is extremely, extremely unlikely. Those are sent back with all of the employee badges, and they are used as the metric. So if there's an exposure on the control badge, then it's not really considered occupational. It's going to be more background. And so it would be deducted from the reading for each individual. Also, there is the possibility that they're exposed in transit. You know, maybe they didn't look at the package or whatever and they ran it through the scanner or the x ray machine. Okay, so once the control's been exposed, that is going to be deducted from everybody else's, so your readings won't come back overloaded. Primary dosimeters should be worn at the collar level, outside the lead apron. For females, the baby badge or the fetal monitor should be worn beneath the lead apron, okay, at the waist level. Now, again, for that badge, we want to know the dose that's gonna that the fetus is actually being exposed to. So we would want it behind the apron as opposed to out in front of the apron. Here are the NCRP recommendations. Your dose limit, your cumulative effective dose limit increases every year. As you get older, every time you have a birthday, your cumulative effective dose limit goes up. So it's your age times 10 millisieverts. The annual occupational is 50 millisieverts. And if you exceed 50 in a year, um, you're going to be put on leave and you won't be able to come back uh, for a period of time. And it also depends on the policy of the facility that you're at. But there should be a radiation safety program in place. Should be a radiation safety officer overlooking that as well. For the general population, the annual is 10% of the occupational. So it's 5 millisieverts. For infrequent exposure, 1 millisievert for frequent exposure. For the entire pregnancy, a radiation worker, their limit is the same as the annual general population. It's 10% of the occupational dose. The fetus, an embryo, is 1/10 of that for the pregnancy worker, but that's per month. Okay, so you know 0.5 times 10 months because that's typically how long it runs, but it won't be because what it'll be probably 2 months before we find out that we're pregnant and we need a monitor anyway. For education and individuals under 18, it's 1 millisievert. The annual dose for lens of the eye is 150, and for skin, hands, and feet, it's 500. Evaluation and maintenance of personnel dosimetry records should be initiated and overseen by the radiation safety officer. We're going to have an ID number associated with each individual, the type of dosimeter that's being used, and records of deep eye, shallow dose equivalents for specific time frames, along with cumulative equivalents for those same three things: deep, eye, and shallow exposure. So here we have a dosimeter report. Let's see here, find this. We're close to 10. I've got two slides after this one. I just want to go over the dosimeter report with you because a lot of people haven't seen one of these, or they haven't been explained how to read them even. So first thing you want to know is these M's that you see here throughout the reports. This stands for minimal reporting service of 1 millirem. Okay. So based on what the control badge had, reporting service of 1 millirem. That's the minimum for these. Mr. Addison has a whole body dosimeter. And for the month of May in 04, this is for this period, deep, eye, and shallow for 31 days of May. The next three columns are quarterly. So this is quarter number 2. So this is going to be for April, May, and June of the calendar year. Then there's a year to date. So January through May 31st, January 1st through May 31st. And then their lifetime from their inception date, when they started keeping record of radiation exposure. Okay, so there's 4 different levels of dose exposure here that you're looking at. So for this month, he had 90 deep. He's got 3 badges here. Okay, had 90 deep, 90 eye, 90 shallow. Those numbers are the same for quarter 2, which means in April he got 0 exposure because it all came in May. The numbers are the same. But from January 1st through May 1st, he only had 10 because we determined all of this is May. 90 minus 100 is only 10. And this is the year to date. So he only got exposed 10 millirem for the first 4 months of the year. Now, lifetime, he's at 200, starting in 97, which that's pretty darn good. Because this is 2004, so that's what? But you'd want to be really cautious about this. That's almost 50% of his lifetime he got in May. So, we'd want to look at that a little bit closer. But you could go through the slides here for you, and you can examine these. If you do find out you have any questions, just shoot them to me, and I'll do my best to answer them for you. But every time you get one, since this is monthly, every month you should have access to your readings. Somewhere in the department, they should post these for you. Go by, take a look. Keep up with what you got. If you change jobs, the company's required to terminate the monitoring for you, and the company, Landauer, will produce what's called a terminal report, which is your lifetime, including your inception date, and it will be sent to either you or your new employer. So that, again, because it is cumulative, you want to have and maintain records of your exposure. The recommendations for the NCRP, there should be a limit or a trigger level that's set by the facility to monitor abnormally high readings. Dose report is part of the employee's record. And again, if an employment change occurs, you should be given or have access to a terminal report to provide to your new employer. And the last slide here, unless you're working in nuke med, it doesn't really apply to you, but it does go over the handling and disposal of radioactive elements. You make sure that if you're handling isotopes in a liquid form, you're wearing a gloves. Don't touch them with a bare hand. A lot of that stuff can be absorbed readily into the skin. You need to be equipped with personnel dosimeters. Follow the cardinal rules of radiation protection. Some procedures will require the isotope to be put back into the lead containers that they were transported in. And that container should be labeled with how much radioactivity remains and the current date. Should be held for a period of 10 half-lives before the isotope can be disposed in regular trash. So depending on the isotope, you'll have to hold it for however long it is. And some of this is in minutes and hours. We're not talking days and weeks in most cases, but it really does depend on the isotope and how much of that material is left over or wasn't used. And that concludes safety. Does anyone have any questions?
Hi, I have a question.
Yes.
So in terms of expectation, of what we're supposed to be tested on from our mock exam that we took a couple days ago, those are similar to the questions that were going to be asked on our exam, correct?
In terms of material, yes.
Okay, the only thing that like concerns me is like I'm doing, I'm again referencing workbooks and like you said in the previous lecture, it's better to be over prepared than under prepared. But the workbooks and the flashcards that I'm using to like try to study are presenting overly difficult questions. And so I'm just kind of confused as to where I should be standing in terms of, should I just know the basics? Should I reference our comp exam in terms of like the questions we're going to be facing? Or do I even, and like you said you have your own gripes with like Lang and Mosby in terms of how they present some of the information, correct?
Yes. What I'm understanding from going to conferences and speaking with the ARRT, um, they do a lot of scenarios um, for a good number of the things that they test over. And so while if if it seems like it's overly difficult, then I would prepare better over that subject.
Okay.
Because really the questions should not be uh they should not be that difficult. Now, if you want to, you find some of those questions or whatever, email them to me and I can give you a kind of an idea of what the level of difficulty is for that question.
Gotcha. Okay, because some of the flashcards, like I opened up the flashcards and I'm like, okay, let me do like a quick little study session when I'm at work, and I kid you not, it was like the wording was so overly complicated and that obviously overwhelmed me. And then looking at our comprehensive exam, it was far simpler. So I was just really confused as to why it's overcomplicating the questions because
Right.
it doesn't make sense.
Okay.
But any of those that like I truly struggle with even after like looking at it a few times and knowing the answers, I'll reach out to you.
Okay, that sounds good. I mean,
Um,
that's probably the best thing because it's a little bit difficult for me to imagine. You
Right,
know,
right.
I would do better with an example. I'm sure,
Okay.
just like you would.
Yes,
Okay.
yes. Thank you so much. I appreciate it.
Yes, ma'am. You're very welcome. I went ahead and I did the lecture and I didn't record it. So what I'm going to do is post um a live lecture recording from the last. So you'll have the benefit of the same slides with a little bit of a different lecture. It's still going to be me. But if you have any questions, again, reach out, send them to me. I'm doing my best to stay on top of them, getting them your answers back and answers back to you. But have a good rest of your Monday evening. Try to stay cool this week. Um, if you're behind, try to catch up. I'm going to try to get through the grade books um, by about 10 o'clock tomorrow p.m. So if there's anything that's outstanding, remember I got to put a 0 until it gets done, and then you let me know that you've completed it, and I'll adjust the grade again. So tomorrow I'll do grade adjustments. So all the RT, RadTech boot camps, the comprehensives, all those sections. If the grade hasn't been scaled yet, it will be Tuesday. Okay. Be safe, and again, stay cool. Y'all have a good night. Thank you for being here. Do 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 do.